Hi, my name is Anesha,
Hi, my name is Vijaya.
and today we're going to talk about developing a predictive model based on health data from patients in order to predict heart disease. So our value proposition for developing a model like this is that it would help patients enact preventative measures against the leading cause of death in the US, which is heart disease. Additionally, it would warn at-risk patients of potential factors that could lead to a heart disease diagnosis and allow them to enact preventative measures. And it would also help patients with limited access to healthcare due to economic barriers know what they're susceptible to and get healthcare on time.
So given our labeled data set, we wanted to do a supervised learning model, specifically classification, to see if we could build a model that would most accurately classify whether or not someone had heart disease, given our various features. So we initially conducted four different models to see which one produced the highest accuracy. We did decision tree classification, linear regression, k-nearest neighbors, and also random forest. And we noticed that random forest had the highest classification accuracy of 89.13%. So given that random forest is an ensemble learning method, it was important for us to also do feature importance to see which feature was affecting our data the most. And feature importance scores indicate how much each feature contributes to our overall performance of the model when prediction. So the higher it was, it meant that it had greater impact on our model's prediction of the classification of the features. So looking at this graph, we can see that chest pain type had the highest feature importance, while fasting SBS and ST slope had the lowest feature importance. And given these feature importance, a little more analysis we did was removing them from our data set to see how it would change our random forest classification accuracy.
So the motivation for pursuing this project was that 1 in 5 deaths in the US are from heart disease per year, which is an alarming statistic, and a lot can be done to solve that. Technology for social good is also something that we've learned in and outside of class, and using machine learning for social good as well, so we wanted to apply those lessons learned in a real life aspect. Additionally, prevention by early detection via a predictive model can be an amazing asset for patients. Heart disease has also been a factor in our own health history and also for many others, so we know that we're seeing people in real time being affected by it, and knowing the warning signs is important for people with infrequent access to healthcare, and in order to do that, a machine learning model would definitely help them.
So when it comes to our problem statement, our P, which is the performance metric, was to test the accuracy of our classification model. Our task T was classifying whether or not a patient has heart disease based on our features, which were different health factors. And E, which is our experience, was the labeled data set that we had that gave features and whether or not a patient had heart disease.
So the data set that we found is available on Kaggle at this link. The data contains 918 rows and 12 columns, and it has no outliers, no duplicates, and no NaN values. So in terms of cleaning, what we mainly had to do was replace data types to things like string, integer, and float, basically whatever suited the values of the data set. And according to the Kaggle website, this data has been used in a few other projects. So over here we can see a breakdown of the dataset's columns. So each of the columns represented a characteristics of the patient. Most of them were medical things, but a lot of them were also just, for example, sex of the patient, and the rest are chest pain type, resting blood pressure, cholesterol, fasting blood sugar, resting ECG, LVH, max HR, exercise, angina, etc. So the values for these were also different. Some were yes and no values, some were numerical. So obviously based on these things, we had to evaluate our data set accordingly. The data also has 918 rows, and each row represents data for a specific patient, either diagnosed with or without heart disease. So therefore we were able to run the machine learning model on these 918 patients. So we also conducted some exploratory analysis to kind of get a feel of the data before we were able to write the model. So one of the main questions that we wanted to explore for this were the relation of sex and heart disease or no heart disease. So as we can see in the data over here on the left, the number of individuals per sex is shown, and it's very clear that there are a lot more, probably over double the amount or triple the amount actually, of males than females in the data, which definitely shows that the data is skewed based on sex, so it might be better in the future to collect data that is a more 50-50 split. Additionally, over here, it's interesting to see that more men were diagnosed with heart disease in this data than women, and more women were diagnosed without heart disease than men. So this was kind of an interesting observation that we were able to make.
We also wanted to look at the correlation between the different numerical factors, and this heat map shows the correlations we determined. And we saw that there are no two factors that are highly correlated, and this was important to look at to make sure that none of our features in the random forest were related to one another, which could be affecting our results. So when it comes to the architecture, the first thing we did was build a base pipeline because some of our variables are categorical and some are numerical. We first did a one-hot encoder for our categorical data and did a standard scaler for the numerical data. We also split the data because it is classified. We used 80% of it to train our data and the other 20% to test data. So after we had this base pipeline, because we also wanted to see which classification method provided the best accuracy, we had the 4 different classification methods. So we had 4 different pipelines for each one. And then specifically for KNN, before we built the pipeline for that, we wanted to make sure to do feature cross validation to determine which K value would be the most optimal for our KNN pipeline. And also, after we determined that random forest does provide the highest accuracy for classification, it was important for us to do feature importance and get more results from that. So following the architecture, it's important to look at the results. And this graph shows how the different classification accuracies were for not only the 4 different classification methods we had, but also after we saw that chest pain type had the highest feature importance and fasting BF and ST slope had the lowest, we thought it would be interesting to see how removing those from the data sets would affect the accuracy of the classification, and that all these results are presented here in the graph. And it's interesting to see that chest pain type has without chest pain type has the highest accuracy.
So this is a further comparison of feature importance, but it's for the 3 random forest algorithms that we ran. One which just showed the regular weight of the features, one without fasting BS and ST slope as we discussed, and also one without chest pain type. So if we look at the red one, which is basically just a regular random forest machine learning model, we can see that chest pain type has the highest feature importance, and everything else is relatively similar. There's not anything that really stands out here, but then as soon as we take away chest pain type, if we look at the blue, suddenly exercise angina and old speak are the 2 highest weightages for feature importance, and these 2 were very low when it came to having chest pain type in the mix, and were also not the second highest compared to the other features. So it was very interesting to see what would happen when removing and adding back different features. The weightage changed in places that we didn't expect. So this was definitely interesting to see comparing the different feature importances for each of the machine learning models.
So overall, when it comes to our results, our initial task was to determine which machine learning model would provide the highest classification and error accuracy, and we saw that random forest provided us with the highest accuracy. Given that we did the feature importance and saw that chest pain type had the highest feature importance. And something interesting we did come across and would be important for us to further explore is trying to understand why removing chest pain type from our data set increases the accuracy of random forest if it has the most important influence on our accuracy.
So for future work, since we've done this research and we've built the model, we have definitely determined that machine learning like this can be used in healthcare to enable the prevention of heart disease and provide signs of early detection. This could also go for other diseases where patients would be able to look at their data in machine learning and determine what's best for them. Additionally, patients who don't have frequent access to healthcare can utilize the output from these machine learning models to know which tests to take and when, and also what they're susceptible to, so that they're not spending their money taking different tests and they're able to kind of narrow down their search to get the best healthcare advice. And additionally, data collection should be ethical in the future when this work is done, and rights should be reviewed before any data is collected or fed into the machine learning model. So things like HIPAA and AMA guidelines are definitely crucial to review, and data samples for any type of diseases should also be more inclusive, so an equal amount of female and male participants with and without the disease, such as heart disease in this case, would definitely be beneficial for all patients to diversify the data set, prevent bias, and get an overall beneficial outlook. So that's the end of our presentation, and thank you so much for watching.